and evening, everyone. Welcome to today's webinar on the evolving building blocks of data streaming. We have two speakers for today's session, Larry Heathcote, who leads product marketing at Ivan, and John Turner, who is Senior Technical Account Manager at Ivan. Now, without further ado, I'll hand it over to Larry to share more about the evolving building blocks of data streaming.
Thank you very much, Karan. Let me introduce both myself and John. So my name is Larry Heathcote. I'm the head of product marketing for Ivan's Core Services. And I've been in the data analytics, data pipeline, streaming business for probably about 2 decades or so. And I've worked with both Fortune 500 companies as well as a number of different startups. John, would you like to introduce yourself?
Sure. My name is John Turner. I'm a senior technical account manager here. Over the past 2 decades, my journey in the tech industry has been focused on navigating the complexities of managing large volumes of sensitive data, with an emphasis on the financial sector. Today, I'm thrilled to be here to discuss the evolving building blocks of data streaming. And I'll pass it back to you, Larry.
Thank you, John. Much appreciated. I'd like to start out today's webinar a little bit differently than I think most webinars are started. I want to start with a customer example. And this is one of Ivan's customers named Avaya. And Avaya has chosen Ivan to help them manage their data infrastructure. Avaya is a global leader in customer experience solutions. They have more than 6 million contact center seats globally. They also support customer experience platforms and solutions. They support 90% of the top 100 US companies, as well as 19 of the top global banks, and also 10 of the top airlines and automotive companies. Now, to set some context, Avaya had been developing their own solutions, but they wanted to move to the cloud. Apache Kafka and OpenSearch were their 2 foundational products. They used Apache Kafka to stream messages between a microservices-driven or event-driven architecture, and they used OpenSearch to store emails and texts for search and analytics. So Avaya chose Ivan to help them move to the cloud and implement Kafka and OpenSearch and move their data there. So what they experienced was a 40% reduction in compute used. Now that's a very, very significant savings. It resulted in 15% better cost management. And another advantage they saw was that they were able to resolve incidents in 30 to 40% less time. But what's even more important to Avaya is that they no longer had to advertise, hire, and bring on very deep technical Kafka skills. And this was a major thing for Avaya. They had been training their staff on Kafka. They were trying to keep them up to date, and it just wasn't working for them. They wanted to take some of those resources and move them to other innovative and interesting activities like working on their experience platform and bring new innovations to their customers. And what they found is they were able to let Ivan manage the data infrastructure for them with Kafka and OpenSearch, and they were able to move resources to work on innovations with their Avaya experience platform. Huge win for Avaya. So what we're going to cover today is really 3 topics. First is the evolving building blocks of streaming. I'm going to go through a little bit of Kafka basics and talk about what it takes around Kafka to assemble those building blocks. And then, John, what are you going to talk about today?
Thank you, Larry. Today, I'm going to cover a few key streaming use cases and the building blocks that are needed for an end-to-end solution. I will also do a quick comparison of Kafka pricing models and share an exciting bring your own cloud model that helps reduce cloud expenditures. At the end, we'll wrap it up by answering any questions that you might have.
Thanks, John. Much appreciated. Well, let's get in and talk about some Kafka basics. So here is a picture of a typical implementation of Apache Kafka. In the center, you have Kafka itself, and you'll see a Kafka cluster with 3 brokers. You'll see the legacy zookeeper that manages a lot of communications and resources within the cluster. Now, on the left, you see producers. Producers are data sources, and they push data into the Kafka cluster that needs to be organized with topics and partitions. Now, each data stream flows into a pre-configured topic, or I guess you would call it a folder, like in a file cabinet. And that topic is then broken into different partitions to handle any volume of data coming in at low latency. Now, on the right, you see consumers. Now, consumers will monitor and subscribe to those topics and data streams. And when data comes in, that data is immediately available to the consumers to use in whatever form that they want. Now, the really key advantage of this kind of architecture is that the producers and consumers run completely independently of each other. They're decoupled, which means they don't need to know anything about each other. Producers simply produce data and push it into Kafka. Consumers simply listen for when data arrives and then consume it whenever they want to. Could be right away, could be after some sort of a delay, but it's completely decoupled from the producers. Okay, with that kind of basics at our fingertips, let's look at some of the challenges of Kafka. Now, in spite of Kafka being pretty widely used, it's still a fairly difficult service to get up and running smoothly, efficiently, and manage it over time. It has brokers. You need to set them up. You need to configure the size, the clouds, the regions that they're in. And that takes a little bit of time. With the operational side, you need to configure a lot of settings within Kafka. How long are you going to retain information? When is it going to be deleted? Is it immutable forever, or is it get automatically deleted after 7 days, 30 days, whatever? It takes a lot of self-management time to apply Kafka patches and upgrades and make sure that the system is running smoothly. Over time, you might find that the broker might need to be rebalanced depending on the amount of data that's being streamed in and what topics those data streams are being fed into. You might also have to rebalance the topic itself or rebalance the partitions within the topic based on the amount of data coming in. And periodically, you want to make sure that you can do an automated health check on the entire system to see if there's additional areas where you can optimize Kafka overall. Now, Ivan takes care of all of these things for you to make sure that your system is running very, very smoothly and efficiently. So it really doesn't have to be so hard. Okay, let's move on and look at the 4 pillars of an open source streaming platform. I hear a lot of talk these days about a Kafka ecosystem, and it really takes more than just Kafka. First, you do need to stream data. You need the ability to produce and consume data via the Kafka or REST API. Secondly, you need to connect Kafka both to your data sources so that they can push data in, and you need to connect to your data consumers who need to who are subscribing to those data streams so that they can act on that data whenever they want to. So the Kafka connector framework needs to connect to popular data sources and sinks to make it very efficient. So that's bringing the sources and the data destinations into the Kafka ecosystem. Then there's the process pillar. Now here we're talking about processing the data while it is in flight. Here we're making millisecond decisions. Maybe we're joining the data with some historical data. Maybe we're aggregating it. we could be performing some simple calculations on that data while it is actually in motion. And we can do that either with Apache Flink or with Kafka Streams itself. And then fourthly, there is the governance of the data. Now, data sources have a certain schema for their data structure, and that schema needs to be set up in Kafka, but data sources are notorious for changing the schema and not letting downstream systems like Kafka or data warehouses or other systems be aware of those schema changes. So schema registry, you can register your schemas, and when the schema registry knows that it's being changed, it can populate those changes within the Kafka system without any problems, just smoothly. Okay, let's look at what this looks like in a real environment. So here it takes the complete streaming ecosystem. You see Ivan for Apache Kafka in the middle of this diagram, and that is the full open source version of Kafka. Now you can download that yourself, but it's so much easier to have an open source managed vendor like Ivan, apply that, deploy it on your behalf, and manage it for you. On the left and the right, you see Ivan for Apache Kafka Connect. And on the left, it's connecting to the data sources. On the right, it's connecting to the data consumers. So connections to those sources and destinations are a big, big part of the Kafka ecosystem. At the bottom, you see Ivan for Apache Kafka Mirror Maker. Now, Mirror Maker is great for data replication. You can migrate data from one Kafka cluster to another. You can use Mirror Maker to replicate your data to a different cloud or a different region and have greater resiliency for your company operations. And that's a great use for Mirror Maker. Now, in the upper left, you see Keras schema registry. This is where the schemas are all registered and monitored, and Claw at the top makes sure that the information both in the schemas and within the topics are well managed and governed for smooth data quality and operations. Okay, but it takes more than just a Kafka ecosystem to really be effective and to help customers achieve their outcomes. It takes a complete data platform. Here you see a simple rendition of the Ivan platform. You've got applications on the top, like business intelligence, running your streaming data pipelines, AI, RAG, microservices architecture, search. You could have any customer applications running up here. The Ivan platform itself has additional observability and AI-driven optimization features to manage your data and your databases to make sure that they're operating at peak performance. It also has additional security and data governance capabilities to manage that securely and consistently across the organization. So the Ivan platform helps stream data, store data in various open technology databases, and serve data out to the applications that need to use it. Now, I've got a number of cloud providers here at the bottom of the slide: AWS, Google, Azure, Oracle, DigitalOcean. And what I want you to understand is that Ivan is completely cloud agnostic. It itself is not a multi-cloud data platform. It is cloud agnostic, meaning that you could deploy Ivan services in one or multiple clouds, and Ivan's platform serves as an abstraction layer above the clouds and above their regions and above the data services to move your data seamlessly and securely to wherever it needs to be. Now, if we look real briefly at the data services that Ivan provides, you see under stream data, there's Kafka and Flink. Under store data, many of the widely adopted open source, open technology databases, both SQL, non-SQL, et cetera. And on the right is just a sampling of the services that we have for serving data. There's OpenSearch, ClickHouse, Grafana, things like that. So you can deploy.
It looks like we may
A
have
couple of
lost
use
Larry.
cases.
Okay.
John, you want to carry on from here?
Yeah. Okay. So essentially, Apache Flink can be used to process the data, transform, filter, aggregate, or join, and then place the data into the Kafka topics. Let's see here. Sorry. All right. Let's begin here. So the real-time data transport. For real-time data transport, Apache Kafka is used to collect, stream data from a source and store the data persistently in another database or analytics system. Here we are collecting real-time data from sources like IoT sensors, operational metrics or log files, change data capture from transactional database like PostgreSQL or MySQL, or any other data stream that may be coming from logistics, supply chain, e-commerce, or web applications. The data is stored in various topics for easy organization and retrieval. The data becomes an immutable copy of the source data. An exact copy of the source data can be recreated at any point in time without any gaps. Apache Flink can be used to process the data and then place the data in additional Kafka topics. Downstream applications for analytics, databases, search, and other applications subscribe to the Kafka streams they are interested in and get the data immediately for further processing, analysis, and other use cases. In this use case, we are gathering real-time data on the left and streaming it into the Ivan for ClickHouse for analysis. The data could be coming directly from Ivan for Apache Kafka or processed, transformed, filtered, aggregated, or joined with Ivan for Apache Flink. The data could also come from a CDC, from a database like Postgres or MySQL, or even come from another data source such as Ivan for Apache Kafka Connect or a customer connector. Ivan for ClickHouse subscribes to various topics to get the data immediately inserted out in an operational dashboard, streaming warehouse analytics, AI, or data science applications. Next slide. An event-driven architecture, EDA, shares data and trigger actions across multiple services and applications. The key advantage is that each service is decoupled from the others, meaning that the tasks execute independently or asynchronously and often in parallel. For example, event data is processed in Apache Flink and set to one or more topics in Apache Kafka in real time. Other services and applications subscribe to the data stream and can read and act upon the data also in real time, or perhaps more importantly, anytime they want to. It is the asynchronous nature that makes the event-driven architecture so unique and powerful. With Kafka and Flink in the middle, this approach is highly fault-tolerant and extremely scalable to handle huge volumes of event data with extremely low latency. Next slide. Let's dive into the heart of our comparison, the pricing model. Understanding the cost structure for streaming is crucial. Starting out with Ivan's costs, they are simple and predictable, ensuring that you have a clear understanding of costs without hidden surprises. Ivan prices per minute for a Kafka cluster, always allocated in dedicated VMs for a consistent performance. If you need more storage, it's priced per gigabyte per minute and there are no partition changes. And Ivan does not charge for networking, so there's no surprises when the amount of data traffic spikes. It's easy to understand and easy to estimate. Ivan ensures transparent pricing without hidden costs or complexities. Other competitors may entice you with a slightly lower cost. It may be a little higher or a little lower than Ivan's, but there's a big catch. Kafka clusters are built with a fixed base cost per hour plus storage per gigabyte hour. The real gotcha starts here. They have an additional partition charge per hour, plus an additional connector cost per minute, plus connectors are billed based upon gigabyte throughput, plus a task-based price per hour. And that makes this even worse as they are charged hourly rates per link, plus additional costs per data sent and received over all the links. And this is what makes some competitors' models so unpredictable. You simply cannot know in advance how much you will be charged. To me, the choice is pretty easy. Simple and predictable versus complex and unpredictable. There is one more differentiating factor between Ivan and other streaming competitors. Ivan allows you to run Ivan services either within an Ivan cluster or run Ivan services in your own cloud account. Our standard model is to deploy Ivan services within Ivan's tenants, providing a seamless experience. Ivan is straightforward with one consolidated bill from Ivan. For data compliance, Ivan includes fully managed security and compliance. In this diagram, we will show Ivan services running in your cloud account, in your tenant, giving you greater control, privacy, and security. We call this Bring Your Own Cloud, or BYOC. All components highlighted in blue are managed by Ivan. In BYOC, you receive separate invoices, one for infrastructure from the hyperscaler and another for managed services from Ivan. Let's take a look at the advantages on the next slide. A major advantage of BYOC is ability to apply your hyperscaler discounts, like cost savings plans, committed or discounted, and other strategies to save 20 to 50% on infrastructure costs. The BYOC model provides additional control and flexibility for customers for specific compliance needs. Data is under your control. It remains in your cloud, allowing you to layer additional security controls on top of Ivan's security and compliance. 3, it's 100% managed open source for provisioning, scaling, and monitoring. Plus, you get 99.99% uptime SLA while leveraging open source technology. Wrapping up our discussion, I want to come back to Avaya. Their Chief Information Security Officer sums up the Ivan advantage quite well. He says that Ivan helps us stay focused on our core mandate rather than having resources stuck on maintenance activities. I think that is a great summary. Ivan is more than just Apache Kafka, and more than just a streaming ecosystem. Ivan is a platform that effectively and efficiently manages your cloud data infrastructure so you don't have to. I hope you enjoyed our presentation today. Now we're going to open it up for some questions. If you have any questions, thoughts, or insights you'd like to share, please feel free to type them into the chat. Your questions are important to us, so please feel free to ask anything. We're here to address your questions and provide any additional information you may need.
Thanks so much, John. That was very helpful.
Thank you so much both for the presentation. I see that we've got a couple of questions, so I'll read it out to you. The first one being, where do you see streaming solutions fitting into the overarching Gen AI narratives?
I'll take that one.
Okay.
So a lot of large language models and AI applications will use batch data to train their models. It takes a tremendous amount of compute power as well as a tremendous amount of data. But what we see happening with a lot of our customers is once that model is trained, they're using Ivan for Apache Kafka to bring in real-time data and fine-tune that model almost in real time in order to edit and revise the prompts that go into the model. So Ivan for Apache Kafka is used quite a bit for that real-time fine-tuning of the prompts for AI. Next question.
Thanks, Larry. And the next one is specific to Ivan platform. So the question is, I would like to run reports showing historic data combined with real-time metrics. How would you propose we do that on Ivan's platform?
John, you want me to take that one too?
Sure, go ahead.
Okay, so Ivan offers ClickHouse as a very high-performant columnar data warehouse, and it can store historical data. But what we see a lot of customers doing is they're also using Apache Kafka to bring streaming data into Ivan for ClickHouse in real time. And this allows any of the users to run their queries and do their analytics both on the real-time data that's coming in absolutely fresh and in real time, and as well as the historic data that's been in ClickHouse. So they're able to get up-to-date answers, up to the second answers, actually, by combining the real-time data with the historical data. Anything else to add, John?
No, I think that summed it up nicely.
All right. I don't see any other questions. So I would just like to thank everyone for their time and participation in today's webinar. If you want to have a more detailed conversation or want a personalized demo, feel free to visit this link and reach out to our team. Our team of experts would be more than happy to talk you through to your use case and show how Ivan can be a data platform of choice. Thank you so much, everyone, again for your time today and participation in today's webinar. Have a great day ahead.
Thank you so much.